Next lecturer is Professor Rob FINLEY of University of Illinois. Professor FINLEY is the director of Advanced Energy Initiative at the Illinois State Geological Survey, Institute of Natural Resource Sustainability. Professor FINLEY is currently leading a big carbon sequestration project in the Illinois Basin, the Midwest Geological Sequestration Consortium. The title of the lecture is Development of an Integrated Demonstration of Geological Carbon Sequestration in Saline Reservoir, Decatur, Illinois, USA.
Thank you, Dr. Murakami. Ladies and gentlemen, well, as you can see, I've actually changed the title slightly because I would like to actually step back for a moment and consider why this hydrogen research is so important on a global basis. And we cannot really consider the hydrogen future if we do not consider the CO2 future and what we might do with the carbon dioxide. I don't have to remind this audience that the Intergovernmental Panel on Climate Change, the fourth assessment report that was published in 2007, pointed out very clearly the accelerating rate of CO2 emissions, or I should say greenhouse gas emissions as a whole, of which CO2 is perhaps the most important component. If we look at the distribution of CO2 emissions in that year, 2004, on a global basis, we do see that CO2 from fossil fuel use accounts for almost 57% of the greenhouse gas emissions. So clearly, CO2 is totally interrelated with our use of fossil fuels, and with the opportunity to substitute hydrogen for some of these fuels, we may be able to concentrate, collect, and store some of the carbon dioxide that's produced rather than having it be emitted by a large number of distributed sources, which is potentially very difficult to control. And further, the IPCC concluded, in their view, and I think the evidence since that time has borne this out, that very much so the anthropogenic contribution, that is man's contribution to the accumulation of these greenhouse gases, is the role that the use of fossil fuel is playing. So every year, as going forward, we add another bar to this graph, which you see here, with CO2 concentration, which is now approaching 400 parts per million in the atmosphere. And each of these years going forward, we see over the instrumental record of temperature, which began in the 1880s through 2010, that each year we add another bar which seems to show that the Earth is indeed warming up in parallel with the increase in CO2 concentrations. And in fact, just a matter of a little more than 2 weeks ago, the U.S. National Oceanographic or U.S. National Oceanic and Atmospheric Administration pointed out that 2010 last year tied 2005 as the warmest year on record on a global basis. So that while the general public often looks at the fact that we've had in Champaign, for example, more snow in December than we've ever had, and we are now, while we are here enjoying the weather in Kyushu, back home we're expecting 35 centimeters of snow in the next 2 days and temperatures below 0 Fahrenheit. So there is a distinction between weather and climate, which is clearly drawn here in this case. So what will happen going forward? Well, absent a policy change, which obviously includes perhaps the different use of energy and the incentive for our use of hydrogen, absent that policy change, CO2 emissions are expected to grow 43% from 2007 to 2035. You see here that the U.S. is responsible for approximately 6 gigatons of emissions on an annual basis. You see that the rest of the developed world, the OECD countries, Organization of Economic Cooperation and Development, that is largely the developed world. Here, of course, it includes Japan, it includes South Korea, Australia, but Europe and the developed countries. You can see that their emissions are relatively level to some extent, but that in the developing world, these emissions will grow strongly. So absent a policy change, those emissions will continue. Why? because in fact the use of fossil fuels is expected to continue, again, absent a policy change and a different approach. 50% increase in global energy use projected, here shown in quadrillion BTUs, going forward to 2035. So clearly we have a challenge in front of us as the demand for energy potentially could contribute to very significant increases in CO2 emissions. And in fact, we're on a course right now where, for example, the current concentrations of carbon dioxide observed already exceed the highest level that we've seen historically in the last 800,000 years, used by a variety of direct and proxy, primarily proxy measurements. But we could be in the next century at a point where we are approaching, perhaps exceeding 550 parts per million, even approaching 900 parts per million, which would be an extraordinary 2 to 3 times the carbon dioxide concentration that we've seen over the last 800,000 years. Looking at Japan, Japan gets 84% of its energy currently from fossil sources, as indicated here, oil, coal, and natural gas. And almost virtually all of that is imported from a variety of sources. So this effort to develop hydrogen and to limit the emissions of carbon dioxide concurrently is a very important effort for Japan. Japan emits approximately 1.2 gigatons of carbon dioxide per year, but interestingly, while ocean sequestration is being actively considered, geological sequestration is also a possibility, and Wright, in their 2005 capacity estimate, indicated that there is geological storage capacity in Japan of approximately 146 gigatons, which would translate to approximately 120 years of output, certainly time enough for us to not only develop and perfect the hydrogen economy, but other sources of energy as well. So what is sequestration? It's sometimes called carbon capture and storage. Basically, we have a source, and this is preferably a concentrated, a major source, for example, a coal-fired power plant, a hydrogen plant that's producing hydrogen to go into a distribution system. We essentially take the CO2 and we put it into a pipeline, and we find an appropriate sink, or, for example, in the case of geological sequestration, a subsurface geological storage site. Geological sequestration is one that a number of the environmental groups in the U.S. have pointed out is potentially feasible, but it also requires several things. It requires basically a highest level, it will receive the highest level of regulatory and public scrutiny, because people are concerned about what you're putting into the ground near where they live, near where they work. And at the same time, it will require a great deal of site-specific characterization and in other words, we have to very much understand the detailed geology, the detailed oceanographic conditions, if we go in that direction, of any location where we consider putting CO2. Well, certainly there are some who say, well, why do we even use fossil fuels? Why do we need to approach this issue of carbon sequestration? Can we not simply use something else, going to green energy, renewable energy, solar energy, and so forth? Well, what you see here and what I would suggest to you is what we really need is a portfolio approach. One single approach cannot really provide the carbon dioxide reductions that are needed going forward, as projected here by the International Energy Agency looking out to 2050. So if we are to reduce the emissions, we need this portfolio, and in fact, carbon capture and storage, as indicated here, CCS, these two components make up approximately 20% of the response. We will not get to the objectives of minimizing climate impacts unless we have this portfolio approach. So there are now around the world a number of major projects that are ongoing, that are actually operational. In Canada, there's a Weyburn project, which is an injection. It's actually an enhanced oil recovery project. One of the longest running projects is I²CNER in Norway. There's a new project in Norway, Snøhvit. The LAC project in France, the Insala project in Algeria, and also one of the newest, and in this case a major commercial project, the Gorgon project on the northwest shelf of Australia. So these projects are starting to take place, and it is something that we can all learn from. The placement and fate of CO2 in the subsurface brings up a number of critical conditions. CO2, of course, lowers the pH of any fluid into which you inject it. It begins to create a number of chemical, geochemical, and potentially geomechanical reactions. So reactive geochemistry is extremely important. We must understand such physical phenomenon as capillary pressure phenomenon, injectivity, reaction with various minerals, because basically for this process to be effective, we must prevent such things as annular flow along the injection well, prevent such things as flow moving through fractures and faults in the surface, because any of these phenomena would render our efforts basically ineffective. So there are a number of really major challenges, and these were outlined in part by the U.S. Department of Energy, Basic Energy Sciences, in a landmark report in 2007, where they pointed to some of what they called the grand challenges in carbon sequestration. Computational thermodynamics of complex fluids, the experiment that I will describe to you in a moment in Illinois, the salinity of the brine into which we are injecting is 200,000 parts per million. There's a tremendous amounts of solutes in place for which with which the CO2 saturated fluids can potentially react. We have to have better integrated characterization and modeling, because we are in effect trying to secure the retention of the CO2 in the reservoir for tens to hundreds of years. So we have to be able to simulate these phenomena, multi-scale geologic simulations over relatively long time frames. At the same time, we are faced with significant limitations on the data that we have available. So let me now turn to our effort in Illinois. Dr. Safronis mentioned the Midwest Geological Sequestration Consortium. We are one of 7 of these consortia which are funded by the U.S. Department of Energy, and we are one of the closest to actually begin injecting, which we hope to inject in either May or June of this year, beginning with 1,000 metric tons of CO2 going into the ground at a site located at Decatur, Illinois. Let's look at a larger scale map. Here is the outline of the state of Illinois. The city of Chicago is here, and our site is approximately 240 kilometers south of Chicago, very close, within a 45-minute drive of the city of Champaign, where the university is located, where the University of Illinois is located. The MGSC, or the consortium, is working with a company called Archer Daniels Midland. They're an agricultural products processing company that is supplying us with the carbon dioxide. Another company, Schlumberger Carbon Services, provides a lot of the drilling and the deep subsurface technology, which I'll show you. And as I indicated, we're going to inject 1 million tons of carbon dioxide at a depth of about 2,100 meters, beginning approximately in 4 or 5 months' time. This is a close-up view of our site. This is the ADM industrial facility here. They process a large number of different agricultural products, and one of the things they do is produce fuel-grade ethanol, which is produced by the fermentation of corn. The fermentation units basically provide us a very pure source of CO2. Our site is indicated here, outlined in yellow. It's a square approximately 800 meters on a side. We've drilled 3 wells, an injection well, a geophysical well, and an observation well at that location. We're located in the city of Decatur, which is, as I indicated, close to Champaign, and is a city of approximately 100,000 people. If we take a closer look at the site, these units, these tank-like units here, these are the ethanol fermentation units. We have built a 4-stage reciprocating compressor facility to basically take the CO2 up to a supercritical state, approximately 10 megapascal output of the compressor system. There is a 2-kilometer pipeline which delivers it to our injection well, which is located here. This, as I indicated, is our site. We share the site with a wastewater treatment facility, a coal storage pile, and an electric power substation. So this is very much an industrial facility. So we have this, all of this infrastructure has been completely developed as part of our effort. In 2009, we completed a 2,190 meter deep injection well. This was a 2.5-month, 24-hour-a-day, 7-day-a-week effort to complete this well. We recovered some of our some samples of our sandstone. Sample recovery is extremely important in this reservoir characterization process because we have to understand the mineralogy of these units. This is a core, a 30-centimeter core. Here you see it looks fairly massive and so forth. If you put it in the X-ray and CAT scan, you can actually see some of the original depositional cross-bedding. This rock unit has 25% porosity, relatively low permeabilities, 43 to 27 millidarcies. But the ratio of these vertical to horizontal permeabilities are extremely important to the distribution of the CO2. So this is our reservoir that we inject into. We must also have a cap rock. So rather than a sandstone, we must have a very low permeability rock, such as this black shale, a 30-centimeter example here. This is a marine shale which covered over this sandstone 600 million years ago to create a reservoir sealed pier that we can use today. We use geophysics very extensively. So again, here's our test site, 800 by 800 meters, the city of Decatur. And this grid here indicates a grid that we use both for samples and putting vibrational energy into the ground. This is what we call in the oil industry a vibe truck. Basically has a large metal plate here that puts vibrations into the ground. We can record those vibrations, and it tells us not only the structure of the reservoir, but it tells us something about the fluids that are in the reservoir, because the response changes depending on where the CO2 is relative to where the brine is. We also drilled a second well in which we cemented at this well much shallower, about half the depth, 1,060 meters. We put 31 multi-component geophones, which are basically vibrational sensors, into the ground so that we can do repetitive surveys which will help show us where the CO2 is as we move forward with injection. So our injection well is here, and this second well was drilled just about 50 meters from the first location. What all of this data can do is provide a visualization that we basically put into the computer. We can simulate the distribution of the different rock types. We can use what's called, for example, an acoustic impedance model to basically predict zones of porosity. We must have porous rock into which we can inject. We can also define, in this case, river channels that 600 million years ago were actually responsible for laying down the sandstone. So this is the type of geologic-based data which is absolutely necessary to ensure that a project like this is successful. Here in Japan, of course, seismicity and earthquakes are important. It's not so much in Illinois, but we nevertheless installed a set of 3 microseismic sensors in our injection wells so that we can take approximately an 18-month baseline of microseismic events. That will give us an understanding of whether or not the injection of fluid as we are doing it has any response in the subsurface. This is an example of the sensors. The sensors were incorporated into one of the pipe strings going in the well. And if there is any alignment, for example, and this is not an example from our site, this is an example from an oil industry application, if there's any alignment of these microseismic events, that, for example, could indicate some kind of faulting and fracturing, something which we would obviously want to avoid. The third well was just drilled and completed 2 months ago. Again, a 2-month, 24-hour operation. And this well was drilled about 330 meters north of our injection well. We obtained a great deal more additional rock material, large 4-inch diameter rock material samples, as well as small samples drilled from the side of the borehole. But most importantly, this well will serve as a first-in-the-world type of observation well in which we will actually take fluid samples for geochemical evaluation and pressure data at 10 different levels, both within the reservoir and above the shale seal. So this particular project is actually unique in the world in terms of being able to predict the safety and security of this type of carbon sequestration, which is essential to successful public acceptance and regulatory acceptance. And bear in mind that I would emphasize that the component of public outreach and education, not only to the general public, but also to regulators and government officials, is extremely important in a case like this. All of these data allow us to develop a number of computer simulations. Here, for example, you see 3 different case studies which were run by Schlumberger Carbon Services with different ratios of vertical and horizontal permeability. Supercritical CO2 is, of course, buoyant. It's notably less dense than the concentrated brines, which are, in this case, 200,000 parts per million brine. So the brighter colors, the reds, indicate the CO2 immediately around the wellbore. You can see that if we reduce the vertical permeability, the CO2 extends out much farther. If the vertical permeability is greater, that the plume grows vertically due to its natural buoyancy. So these are the kinds of things that we must predict in order to understand the fate of the CO2 and make sure we have a secure environment. Of course, shallow environmental monitoring is important as well. We have a number of groundwater wells which cover the entire area around our site, in part because this, for example, is a community college. There are residential subdivisions further to the northwest. So we must be able to demonstrate to the general public that such resources as groundwater is protected and is not being affected by the type of work that we're doing. We also examine soil flux. We also examine electrical resistivity to understand the near-surface distribution of fluids, and we carry out atmospheric monitoring. The well drilling, we have a combination of both deep groundwater wells, by deep here 140 meters, shallow groundwater wells, by which I mean 40 meters. All of these wells are equipped with downhole pumps, so the researcher can simply come and easily take fluid samples. We sample these on a monthly basis, so we not only see the natural annual cycle of CO2 diffusion and respiration, if there is any in these shallow groundwater, imprint of that in the shallow groundwaters, we can basically prove going forward that our CO2 is not present. The air sampling site, this work is being done in cooperation with Lawrence Berkeley Lab. It's an eddy covariance type of approach where you have an infrared CO2 device on the top of a 10-meter tower, which basically looks at the CO2 flux in a large footprint of the area around our site, again, to make sure that after we begin injection, we don't see any indication of CO2 leakage. Let me conclude and make one final point. I would also point out the importance of water. We have another group that is working in collaboration with our Geological Sequestration Consortium, looking at the needs for water. And I would point out one important point here. An equivalent 420 megawatt coal to hydrogen gasification plant with CO2 capture using any of the conventional technologies will require 3.5 million gallons of water per day, both for processed water, for water related, for example, to steam reforming of a hydrocarbon, if that's the approach to hydrogen production. So we must not only consider what we will do with the CO2, we also must consider where will we get adequate water to make these processes move forward and allow us to produce the hydrogen that we expect, particularly if we are going to, at least initially, use hydrogen production from some of the characteristic approaches that have gone on in the past. That includes steam reforming of natural gas, or it also includes gasification of coal or biomass, or both in some cases as a related feedstock. So let me conclude then. What are the potential ways forward? And Dr. Safronis mentioned some of these this morning, and there are certainly perhaps many others. Exchange of scientists was mentioned this morning to further the goal of the I²CNER research. We have data sets that are developed from the MGSC test site, which could be utilized by researchers both here and in the U.S. There may be potential add-on projects, for example, that we are not specifically funded to carry out. These could be various modeling projects. These could be geochemical investigations. They could be other types of investigations that's based on the investment, which for DOE, the total funding for MGSC is $94 million starting in 2003 and continuing through 2015. So it's a major effort to drill these wells. For example, the injection well with all of the hardware and sensors and so forth, that was a $9 million effort just in and of itself. So we would certainly want to maximize the opportunity to having made that investment of funding. My colleague Sally Greenberg, who's the Assistant Director of the Advanced Energy Technology Initiative, is heading up the arrangements for the International Energy Agency Greenhouse Gas Summer School, which will be held at the University of Illinois in July of this year. There's an application period for graduate students, which closes on February 28th. So, Sally, Could you raise your hand if there is any interest there from any of the members here in the audience who have graduate students or graduate students who are interested in doing that? They can certainly get more information on that. And finally, Dr. Murakami had the pleasure of his attendance at one of our past meetings last fall in September with our annual meeting for our regional partnership. This year we will expand our annual meeting to a 3-day symposium which will be held in November, and we certainly invite members of the I²CNER group to come to that and find out more about the work that we are doing and look for potential collaboration that we all hope to gain out of this effort. So thank you very much, and you may certainly email me if you have any additional questions, or you also may go to our website, which is sequestration.org, to find out more about the projects that we have underway. Thank you very much.
Thank you, Professor Finley, for your very impressive lectures. Looking at your data on CO2, I felt guilty with my personal CO2 emission by driving cars. The official discussion for your lecture will be given by Professor Tetsuo Yanagi, the director of the Institute for Applied Mechanics of Kyushu University.
Thank you, Professor Finley, for your nice, stimulative talk. I have 2 questions. Okay? In your case, you just say the groundwater underground is very stable compared to Japan. At the point that we have so frequent earthquakes. So first point is, how do you think about the effect of the frequent earthquake to the geological CCS? The next point, yeah, please.
Yeah, no, please.
Okay, the second question is, in case of the ocean CCS, the acidification is the most serious problem. So I ask to you, how about the effect of the acidification of the groundwater by the geological CCS? It's 2 questions.
Okay, those are 2 excellent questions. In the case of the earthquake question, actually it turns out that southwest of Illinois in the state of Missouri is one as a result of 2 very large earthquakes in 1811, I believe. There is very significant earthquake risk in the mid-continent of the U.S., which not many people know about. And in fact, one of the reasons we're carrying out our experiment where we are is we just want to be a little bit careful. But frankly, I think those kinds of risks can be mitigated. There's really 2 things you have to be careful of. You do not inject into any fluid into a fault system itself, because the fluid, whether it's supercritical CO2 or even water being disposed of, can basically lubricate the fault plane, leading to slippage, resulting in an earthquake. So the approach has to be, as I indicated, as the non-governmental organization I²CNER Task Force indicated, site characterization is extremely important. And we rely on geophysics, for example, very detailed geophysics to look for any major fault planes, regional studies to make sure that the site is safe. And as long as we're not injecting into a fault plane, and as long as we do not drill any well, for example, an inclined well or a horizontal well, that crosses a fault plane that could lead to shear and failure of the well structure itself, actually we have good indications that these types of facilities can actually withstand earthquake stresses quite well. So it's a matter of site characterization. As far as acidification goes, again, it's site characterization. We are injecting at 2,000 meters. The potable groundwater that we are actually monitoring and required to monitor by the regulator is at 40 meters. So, and immediately above our reservoir, we have 100 meters of shale, which is very low fluid transmissivity. We also, within 10 kilometers of our site, for example, we have oil resources at about 1,000 meters in depth, and that oil has been in place for 300 million years. So we have good reason to believe that the geological containment, as long as we don't have man-made penetrations like bad wells or wells that are poorly cemented or wells that we don't know the location of, we have to select a site carefully to make sure that we avoid the acidification of groundwater. The acidification of groundwater is not a given and necessary outcome. It's one that is avoided by careful geological site selection. And over the long term, of course, capillary trapping, dissolution of the CO2 in the brine, and ultimately mineralization, for example, to form carbonate minerals, where basically you may have dissolved iron, magnesium, calcium, brought them into solution, and essentially precipitation as carbonates over the scale of tens, let's say hundreds to thousands of years. That is the ultimate stability that you can expect with CO2 geological sequestration. Okay.
We thank all our keynote speakers and official discussers, and thank you for your cooperation. Now we close this keynote lecture session. So thank you very much for your cooperation.